10,000, as I outlined in my previous video, is a very homey number. 10,000 kilometers will take you 1/4 of the way around the Earth, and most of the longest distances on Earth fall within that range, with two exceptions: up and down. The Earth is only 12,742 kilometers in diameter, so it is impossible to dig down 10,000 kilometers. Down ends at the center, the point towards which all gravity pulls. Digging so far past the center would not place you 10,000 kilometers down, but 3,629 kilometers down from the other side. The situation only marginally improves if you try the other direction. 10,000 kilometers straight up sends you to the outer limits of what could rationally be described as Earth. At that altitude, for lack of a better word, the exosphere, the residual wisp of hydrogen, helium, and carbon dioxide that forms the outer region of Earth's atmosphere, merges with the solar wind. But the Earth's gravity only begins to give way to the gravity of the Moon beyond the two worlds' 1:4 orbital resonance, or the point at which an object would orbit the Earth 4 times for every one lunar orbit. That lies at 144,688 kilometers, or slightly less than a third of the Moon's distance. The halo of incandescent hydrogen atoms, known as the geocorona, is still visible even at 100,000 kilometers. Geostationary orbit, the point at which an orbiting body exactly traces the spin of the Earth, lies at 37,786 kilometers. Our nearest celestial object, the Moon, lies 10 times farther out still, at 384,400 kilometers. But that is nothing compared to the distance to our closest planet, Venus, which, at closest approach, just touches 40 million kilometers from Earth. Space, in other words, is immense. There is no means to reduce it to a human scale, and most illustrations don't even try. Take this image of the solar system. It, like nearly every other, is a lie. The planets are not evenly spaced apart. In fact, the distance from Saturn to Uranus is nearly equal to the distance of Saturn to the Sun, and the distance of Jupiter to the asteroid belt is also nearly equal to the asteroid belt's distance from the Sun. For measuring solar distances, astronomers abandon the kilometer for a less intuitive measurement, the astronomical unit, or AU, which represents the average distance between the Earth and the Sun. But the AU is still an awkward fit for our solar system. The first 4 planets all lie within 2 AU of the Sun, while the last planet, Neptune, is a full 30 AU out. The Kuiper Belt, the circumstellar disk surrounding the charted regions of our solar system, is 20 AU across, while the farthest object observed from Earth in our solar system, a dwarf planet appropriately nicknamed Far Out, is 120 AU away. 120 AU also marks the point at which the solar wind, the bubble of plasma blown into space by our Sun, hits the winds of the interstellar medium. But even then, we are far, far from the edge of the solar system. The Sun's gravity is believed to give up to the gravity of other stars not at 10,000 AU, but 100,000 AU. At that distance, a huge spheroidal cloud of comets, the Oort cloud, is believed to reside, the source for all long-period comets, like Hale-Bopp, that occasionally grace our skies. So where would 10,000 AU take you? In short, we don't know. Nothing in our study of the solar system, either observed or inferred, has taken us out that far. Even Planet 9, the planet proposed to explain the extreme orbits of the farthest trans-Neptunian objects, is only believed to be roughly 800 AU out at the most. But we know the Sun still holds sway there. There may be at that distance dark, lonely shadow worlds making their eon-spanning way around our Sun, awaiting the eyes of future generations. Future planets there may be, but the AU will not take you to the stars. The nearest star system to the Sun, Proxima Centauri, is 268,000 AU away. To get there, you need to make another leap. I'm sure you're familiar with the light year. As a unit, it couldn't be more self-explanatory. It is the distance one would travel in a year if one could do the impossible and move at the speed of light, which, according to our current laws of physics, nothing with mass can attain. It is, as any pedant will tell you, a measure of distance, not time, but in an odd sense, the light year measures time as well. Because all information comes to your eyes by light, When you look at an object 100 light-years away, you see it as it was 100 years ago. How far away an object is determines how far back into the past you see it. There are relatively few stars near the Sun, but as you move farther out, their number increases geometrically. At 10 light-years, there are 14 stellar objects known. At 100 light-years, there are about 14,000. At 1,000 light-years, 10 million, and at 10,000 light-years, 10 billion. These estimates are extremely rickety, however, because red dwarfs, the stars which make up 70% of those we've observed close to our Sun, are too dim to be observed at that distance. Only the brightest, most raging stars can be seen across galactic distances. In fact, no stars you can see with the unaided eye are as far as 10,000 light-years away. Many sources cite V762 Cassiopeae, a variable red supergiant that was once considered about 16,000 light-years away, as the farthest naked-eye star. However, a parallax measurement, I'm getting to that, in 2007 by the Hipparcos probe showed that it was in fact less than 2,800 light-years away. With that one out of contention, the next most solid candidate is probably AH Scorpii, another red supergiant variable 7,500 light-years away, and one of the largest stars known, with a radius 1,000 times larger than the Sun. No one knows the source of its variability, though it may be related to the great cloud of silica dust currently orbiting it. A more famous, if less consistently visible, star at a similar distance is Eta Carinae, a double star system so apocalyptic it has its own nebula of material exploded from its surfaces. Between 1837 and 1856, Eta Carinae brightened to the second brightest star in the night sky, before fading below naked-eye visibility. To reach such a brightness at such a distance, the primary star of Eta Carinae would have to have attained a luminosity 50 million times that of our Sun, bright enough to turn the skies blue on Planet 9. This monstrous variability can mean only one thing. Eta Carinae is about to go boom. Indeed, if Eta Carinae had been any other star, such an increase in brightness would have counted as a supernova. Thankfully, whatever cyclopean dissolution ultimately undoes Eta Carinae, I'm hesitant to describe it as a mere supernova, is unlikely to affect Earth. Its pole is facing away from us, and since supernovae eject most of their energy from their poles, we will likely be spared the worst. But I'm afraid, in a universe such as our own, 10,000 light-years will not get you to the suburbs. It would barely take you 10% across the width of our galaxy. Indeed, it barely covers the maximum width of its disk, if one includes the diffuse outer shell. Most of the notable objects observed in the 10,000 light-year range are nebulae, diffuse clouds of dust and hydrogen that are both the cradles and the coffins of stars. Eta Carinae's nebula sits within the Carina Nebula, even larger than the better-known Orion Nebula, but less famous due to its southern location. Another nebula at a similar distance is G34.3, a small cloud about 3,000 AU across that is believed to comprise 7.6 septillion liters of ethanol. Yes, the alcohol you drink, enough to fill Earth's oceans 6,000 times over. So, 10,000 light-years will not see you out of the Shire. But then, astronomers seldom use the light-year amongst themselves. They see it primarily as a teaching tool for the general public, because it is easily and intuitively understood by the layman. To one another, astronomers speak in parsecs. A parsec, or parallax second, is the distance at which an object's parallax is equal to 1 second of arc. A second of arc is 1/60th of 1/60th of a degree, or about the width of a human hair seen from 30 meters away. Parallax, as I have mentioned before, for obvious reasons, is the apparent shift in the position of a star as it is viewed first from one side of the Sun and then the other. You can see this play out in a microscale if you hold a pencil in front of your face, close one eye, and then another. The pencil will appear to move relative to the background. The farther away an object is, the smaller its parallax, and this relationship is the only direct means to measure astronomical distances. By measuring a star's parallax, you can get a precise value for its distance from your eyes. A parsec, the distance at which a star's position appears to shift by the width of a human hair at 30 meters, is 3.26 light-years. And here's the kicker. No star in the universe is as close as 1 parsec. The closest, Proxima Centauri, is 1.3 parsecs away. Because it requires the least amount of calculation, astronomers prefer to keep their distances in parsecs, rather than convert them into more generally comprehensible units. 10,000 parsecs, or 10 kiloparsecs, is a heftier distance than 10,000 light-years, to be sure. It is, for instance, slightly longer than the Sun's orbital distance from the center of the Milky Way, a trek it takes 225 million years to complete. At that distance lies the 5 kiloparsec arm, so named because it is 5 kiloparsecs out from the other side of the center, which is home to a cluster of high-energy X-ray pulsars. 10 kiloparsecs is also the rough orbital distance of the Canis Major Dwarf Galaxy, which, depending on who you believe, is either the closest orbiting galaxy to the Milky Way, or the remains of a galaxy it has already devoured. To observe objects at that range, smaller than galaxies, nebulae, or super-bright stars, astronomers rely on microlensing events. A magical quirk of Einstein's universe, gravitational microlensing allows space-time itself to act as a telescope. Because gravity bends light, the gravitational fields of exceptionally massive objects will pull the light from objects behind them into visibility, dredging up otherwise hidden objects from the cosmic depths. Unfortunately, microlensing events rely on the momentary alignment of two objects in space, and so are one-time occurrences. One revelation of microlensing at 10 kiloparsecs is the double star system Macho 1997 BLG41, which comprises an orange dwarf orbited by a red dwarf, which was initially believed to be orbited by a large planet, though this was refuted by later studies. That said, most of the most distant exoplanets known have been found using this technique, including one of my personal favorites, Ogle 2005 BLG 390LB, an icy super-Earth about 7.5 kiloparsecs away, affectionately known as Hoth. The most distant exoplanets ever discovered, however, both at roughly 8 kiloparsecs, were detected using the more standard transit method, or in layman's terms, staring at a star until a planet moves in front of it. Sweeps 11 and Sweeps 4, as they are known, are both hot Jupiters orbiting sun-like stars, making them, aside from their extreme remoteness, perfectly ordinary. 10,000, then, is not a practical number when attempting to traverse the universe as we know it today. In intergalactic terms, it barely gets you out of the driveway, and there really aren't any other units we could use at this point. The kiloparsec does extend farther into megaparsecs and gigaparsecs, but the next unit in common use is the Hubble length, which at 14.6 billion light-years is already a sizable portion of the observable universe. The kiloparsec does extend farther into megaparsecs and gigaparsecs, but the next unit in common use is the Hubble length, which at 14.6 billion light-years is already a sizable portion of the observable universe. Even the ancient Greeks seemed to grasp the limitations of 10,000, or a myriad as they called it, for describing reality. The largest number they routinely used, the myriad, or 100 million, wouldn't have counted the number of people on Earth at that time. In around 200 BC, the mathematician Apollonius of Perga attempted to remedy this by extending myriad into higher powers. The ancient Greeks expressed numbers using letters of their alphabet. Myriad was represented using a capital M, or mu. Apollonius represented a myriad as a capital mu with a superscripted alpha, while a myriad, or 10,000 cube, was represented with a superscripted beta, and so on. Other numbers could then be added alongside to give more exact figures. So, for instance, the number tau omicron delta, or 964, could be placed beside mu alpha to create the number 964 myriad, or 96,400,000,000. But even this system had its boundaries. Assuming a standard set of 24 Greek letters, the highest number you could create with such a system would be a myriad to the power of 25, or 10 to the 100 minus 1. 10 to the 100 actually has a rather familiar name, a googol, and it says something about our modern culture's familiarity with large numbers, that name was coined by a child. To Apollonius, that number must have seemed unimaginable. And yet, if people think of it today, it is usually merely as a stepping stone to an even larger number, a googolplex, which is 1 followed by a googol zeros, a number so large that you wouldn't be able to write it down even if you filled the entire observable universe with ink. And as we shall see, the limits of our theoretical understanding comprise numbers of which Apollonius could not even conceive. But among the ancient Greeks, there was one man who did, and his name was Archimedes of Syracuse. Intellectual prowess is hard to quantify, but if measured purely by amount accomplished with the knowledge and tools available, Archimedes must rank as one of the greatest scientific minds in history. He was born sometime after 300 BC in the Greek city of Syracuse, in what is now Sicily, the son of an astronomer. His name means master of thought, and so it is unlikely to have been his actual name, but rather an honorific bestowed upon him by admirers. In his youth, he studied at Alexandria, where he likely met his friend and correspondent Eratosthenes of Cyrene, the mathematician who calculated the circumference of the Earth. Archimedes was one of the first people to apply mathematics to what we now call science. He is perhaps best remembered for Archimedes' principle, which the man himself states as, quote, "Any object, totally or partially immersed in a fluid, is buoyed up by a force equal to the weight of the fluid displaced by the object." In other words, the more fluid an object displaces, the more the upward force of the fluid acts upon it. That is why kilogram-sized iron lumps sink, while kiloton-sized iron ships float. The ship weighs far more than the lump, but because the ship has a higher volume relative to its weight, it displaces more water, and so is acted on by more upward force. According to legend, Archimedes discovered this principle while trying to perform a favor for the king of Syracuse, Hieron II. Hieron had commissioned a local artisan to fashion a crown of pure gold to adorn the statue of a deity, but he had begun to suspect the goldsmith had cheated him by doping the crown with silver. Archimedes went home and, while relaxing in a bath, noticed the water rise as he settled in. Overcome with inspiration, he jumped out of the bath and ran naked and dripping through the streets, screaming, "Eureka!" which is Greek for, "I have found it." He reasoned that, since a fake crown would have a lower density than an equal volume of pure gold, then, like a ship, it would displace more water. This story is very likely false. Centuries later, Galileo pointed out that the measuring tools of the time were far too crude to make such a determination. But nonetheless, it does speak to Archimedes' reputation as the epitome of the absent-minded professor archetype. A somewhat contradictory account of Archimedes claimed that, when immersed in abstract scientific thought, he would have to be violently carried to a bath or anointing room, and when being bathed, would often draw geometric figures in the soap. Archimedes was famed throughout the known world for his inventive genius. For instance, he designed the Syracusia, a gigantic ship believed to be the largest transport vessel constructed in antiquity. The ship reportedly weighed 2,000 tons and contained a library, a gymnasium, a hot bath, and a temple. Too large to dock at any port in Sicily, it was offered as a gift to the king of Egypt. The ship's size made leaks inevitable, so Archimedes devised what we now call Archimedes' screw to expel the bilge water. Variations on this invention are still used today. His investigations into the principle of the lever reportedly led him to declare, quote, "Give me a place to stand, and I will move the earth." In another likely apocryphal story, Hieron challenged Archimedes to demonstrate that claim, whereupon he constructed a lever system that lifted the Syracusia, fully laden, into the sea. Upon seeing this, Hieron supposedly declared, quote, "From this day forth, Archimedes is to be believed in everything he might say." Incidentally, to move the Earth 1 micron, with a fulcrum 1 meter away, would require pushing a lever long enough to reach the galaxy NGC 300 for 2.6 parsecs. Assuming a downward push speed of 1 meter per second, the action would take 2.5 billion years to complete. But Archimedes was powerless to change the world in which he lived. His home city-state, Syracuse, despite being in Sicily, was very much part of the Greek world, a distant outpost caught between the dominant naval power of Carthage and the rising power of Rome. The goal of complete dominion over the Mediterranean would eventually bring these two powers to blows, with Syracuse an inevitable casualty. Hieron had risen to power without bloodshed and was determined to preserve peace at any cost. In a fortunate political gamble, he sided with Rome in their first war with Carthage, leading to decades of peace. During the Titan's second clash, however, the Carthaginians, under Hannibal, would annihilate Rome's forces at the Battle of Cannae, leading to intense political pressure for Syracuse to switch sides. In 214 BC, Hieron's grandson, Hieronymus, was assassinated by the pro-Carthaginian faction, and in response, Rome declared war on Syracuse. The Romans must have viewed the conquest of Syracuse as a pleasant jaunt in the park. It was a tiny city, a skip across the pond from their home territory, but they had reckoned without one unforeseeable element. Rome had an army rapidly evolving into the most formidable and tactically advanced war machine the Western world had ever seen. Syracuse had Archimedes. Now in advanced old age, Archimedes turned his ornate contraption of a mind toward the defense of his home. Accounts speak of Archimedes' claw, a contraption based on levering principles that could tip ships out of the water, or of a mirror that concentrated the sun's rays into beams that burned ships' sails. Much as I love the idea of Archimedes confronting the Roman legions with laser cannons, there has been some debate about whether such an invention was actually possible. His most effective invention was simply to stagger the ranges of his catapults, so they fired at shorter distances as the ships approached, thus extending the drop zone all the way to the shore. Unable to see the operators of these seemingly magical devices, the Romans, according to Plutarch, began to wonder if they were fighting gods. But Syracuse, unfortunately, overplayed its hand. Believing the siege all but won, it decided to hold a festival to the goddess Artemis, during which nearly everyone would be sloshed out of their minds. Doubtless taking a cue from mythology, a small group of Roman soldiers scaled the walls under cover of night to let in reinforcements. While the city was comprehensively sacked, Marcellus, the Roman general in command of the siege, was understandably eager to capture Archimedes alive. Unfortunately, Archimedes' nature would be the end of him. A Roman soldier unwittingly came across him while he was drawing geometrical figures in the sand. After he protested that the soldier had walked over his careful diagrams, the soldier promptly killed him. According to legend, Archimedes' last words were, "Do not disturb my circles." However much of a techno-wizard Archimedes may have been, he left no account of his astonishing achievements himself. All such tales were written by others. Archimedes considered himself a mathematician first and last, and he was very good at it. His use of the infinitesimal anticipated the development of integral calculus 2,000 years later. He was the earliest known mathematician to develop an algorithm for calculating pi, which would remain the standard for over 1,000 years. He was the first to show that the area of a circle was pi r squared, and the first to formulate the equations for the volume and surface area of a sphere. For all that, though, it is on one of his simpler speculations that I wish to focus. Psametes, usually translated as the Sand Reckoner, is a markedly short work. The free English translation barely covers 8 pages. It takes the form of a letter to Gelon, the son of Hieron II, in which he sets out to disprove the axiom that the number of grains of sand in the world is uncountable. In fact, he asserts that not only is the number of grains of sand in the entire world countable, but the number of grains of sand in a volume equivalent to the entire known universe. To the ancient Greeks, the universe was a giant spherical shell dotted with a spray of lights called the fixed stars. Below these fixed stars were the orbits of the higher planets, Saturn, Jupiter, and Mars, and then the Sun. Below the Sun were the planets Venus and Mercury, the Moon, and at the center, the sphere of the Earth. But Archimedes was not interested in the cozy, clockwork, geocentric universe of his time, with its interlocking spheres of planets all nestled in an eggshell of fixed stars. Archimedes would show that he could count a universe grander and wilder than that. For his hypothetical universe, he chose the, to the Greek mind, gargantuan alternate vision of Aristarchus of Samos, who was the first to suggest that the Sun was immobile and that the Earth revolved around it. Incidentally, the Sand Reckoner is the only work we have that mentions Aristarchus' heliocentric belief. The Greeks already knew that, to quote Ptolemy, the Earth was as a point to the heavens. For no matter where you traveled on the Earth's surface, the patterns of the fixed stars showed no parallax. If Aristarchus was right, which, just to be clear, he was, though Archimedes would never know that, then the entire orbit of the Earth around the Sun, and by extension the orbits of all the other planets, must also be as a point to the fixed stars, which would mean the fixed stars lay beyond a black, empty cavity of almost inconceivable vastness. Almost inconceivable. To begin his treatise, Archimedes claims that the circumference of the Earth is 300,000 stadia. A stadion, or stade, was about 176 meters. This is a surprising figure, given that he knew Eratosthenes of Kyrene, who had determined the far smaller and more accurate value of 250,000 stadia. It's possible, if unlikely, that Eratosthenes hadn't made his measurement by the time the Sand Reckoner was written. Regardless, Archimedes renders such quibbles pointless by blowing the Earth up to 10 times its circumference and declaring it 3 million stadia. Because, big. He then takes Aristarchus' estimate for the diameter of the Sun of about 20 lunar diameters and goes wild with it, jumping it all the way to 30 lunar diameters. The actual number is 400 lunar diameters, so bit timid there, Archie. To be fair to Aristarchus, his method for determining the Sun's diameter was mathematically sound. Aristarchus determined that when the Moon was half full, it lay at a 90-degree right angle between the Earth and the Sun. If the Sun were infinitely far away, then the angle between the Earth and the Sun would also be at a right angle and the lines would never meet. But if the Sun were a finite distance away, then the lines would eventually converge, forming a triangle. The angles of a triangle add up to 180 degrees, so all Aristarchus had to do was measure the angle between the Earth, the Sun, and the Moon, and whatever was left over from 90 degrees had to be the angle at the top of the triangle. Aristarchus didn't have trigonometry to help him, but with all the angles he could provide a distance to the Sun in lunar distances. By tracking the Earth's shadow over a lunar eclipse, Aristarchus knew that the Moon took about 4 hours to cross the diameter of the Earth, which meant that the radius of the Earth, half the diameter, had to comprise about 2 hours of the Moon's 29.5-day orbital period. This in turn meant that the Moon's orbital circumference had to be about 377 Earth radii, and thus that its orbital radius, or distance from the Earth, was roughly 60 Earth radii. Since the Moon perfectly covers the Sun during a solar eclipse, however many times farther away the Sun was from the Moon must also be how many times larger its diameter is. Aristarchus measured the Moon-Earth-Sun angle at 87 degrees, meaning that the Sun had to be 20 times farther away than the Moon, and thus 20 times larger. He may have been wrong. The actual angle is closer to 89.9 degrees, but you could call that a first attempt at a minimum distance. Through an immensely complex series of geometrical calculations, Archimedes was able to show that the diameter of the Sun was greater than one side of a 1,000-sided polygon inscribed on the circumference of the universe, which he defined, for some reason, as the sphere with the radius of the distance between Earth and the Sun. This is true, by the way. The Sun's diameter is slightly larger than 1/1000th the circumference of Earth's orbit. Using his vastly inflated diameter from the Earth as his starting point, Archimedes computes the universe as a sphere with a diameter of 10 billion stadia, or about 1.6 billion kilometers. Somewhat ironically, given how vastly overstated Archimedes intended his numbers to be, that would comprise a circle only slightly larger than the orbit of Jupiter. And here is where 10,000 finally comes into play. Archimedes then proposes a far more easily countable unit, poppy seeds, as a convenient divisor, and asserts that one poppy seed volume cannot contain more than a myriad sand grains, which, assuming a standard minimum diameter for a sand grain of 0.2 millimeters gives you about 4,000 per poppy seed, is a fair estimate. He then asserts that 40 poppy seeds span 1 finger breadth, an assertion I cannot test at the moment as I have no poppy seeds. And then Archimedes begins to count. He calls a myriad, or 100 million, the traditional end of the Greek number system, the first order. The second order comprised units of the first order, that is, multiples of a myriad, and counted them up to a myriad, reaching a myriad, or 10 to the 16, better known today as 10 quadrillion. He called that number a unit of the third order. He then counted units of 10 to the 16 up to a myriad, or 10 to the 24, and so on, all the way up to the myriadth order, or 100 million to the power of 100 million. That is, 1 followed by 800 million zeros. Even Google's calculator gave up on that one. For his task, however, Archimedes had little need to go so far. Despite having worked out how to determine the volume of a sphere himself, he decided simply to cube 40 to get the base number of poppy seeds, and then to multiply that by a myriad for a total of 640 million sand grains per cubic finger breadth. Archimedes then asserted that a myriad finger breadths were equal to 1 stadion, and since his diameter established for the universe, the cozy, geocentric, non-Aristarchan one, was 10 billion stadia, Thus, the total number of grains of sand contained in a volume the size of Archimedes' definition of the universe would be less than 1,000 units of the seventh order, or in modern terms, 10 to the 51. But Archimedes wasn't aiming for cozy. He wanted to see what Aristarchus's vast, empty cosmos could hold. Archimedes had defined Aristarchus's universe as one in which the orbit of the Earth around the Sun had the same ratio to the outer shell of fixed stars as the mere sphere of the Earth had with the outer shell in the standard cozy universe. And since the ratio for the Earth to the edge of the cozy universe was 10,000 to 1, it followed that the ratio of Earth's orbit to the edge of the cold, black Aristarchan universe was also 10,000 to 1, or 10,000 times 10 billion stadia. That creates a sphere with a radius of 59,000 AU, or a fair approximation of the size of our solar system out to the inner wall of the Oort cloud. This diameter left a final number for the grains of sand required to fill the universe at 10 million units of the eighth order, or 10 to the 63. Oddly enough, thanks to its power being a multiple of 3, that number has a name, a vigintillion. Even my spell checker knows it. But as I said, such a number only encompasses our rustic solar system. What of the universe that we know, and which Archimedes could only have dreamed? Well, here we are caught in something of a bind, for there are limits beyond which even we cannot know. What we call the universe is really the fragment of the universe that we can see, the so-called observable universe. And within it, we are trapped by the finite speed of light, by whose grace we are able to see anything at all. Since the universe was born 13.8 billion years ago, we can only see those events whose light has reached us in the last 13.8 billion years. That does not mean, however, that the observable universe is 13.8 billion light-years across. The expansion of space-time, as observed by Edwin Hubble, is not bound by Einstein's equation, and, in the 13.8 billion years since it began, is estimated to have blown the observable universe to the staggering size of 93 billion light-years, or 28.5 gigaparsecs. So how to fill it with sand? Actually, chance has made the conversion surprisingly easy. 59,000 AU is close enough to the 63,000 AU that make up a light-year as makes no odds, so the vigintillion grains of sand in Archimedes' universe could be said to fill a cube with a side length of 2 light-years. Come on, I'm not being any sloppier than he was. A cube with a side length of 2 light-years has a volume of 8 cubic light-years, which is pretty close to 10 cubic light-years. If we assume the observable universe is a sphere with a diameter of 93 billion light-years, that creates a volume of 42 nonillion cubic light-years, or 4.2 nonillion sand universes. All that's left then is to add the exponents together and produce a final number of 4 times 10 to the 93 grains of sand. A number I believe is called a trigintillion. But come on, we are modern Homo technius. Surely in 25 centuries of expanded awareness, we can move beyond sand. There must be a unit more befitting of our grand, ever-expanding horizons. Well, there is. In fact, you could argue that it defines those horizons. We call it the Planck length. The Planck length is defined by 3 basic universal constants: gravity, the speed of light, and Planck's constant. Anyone vaguely familiar with Einstein's ideas will know the first 2. Gravity is the universal force by which every substance in the universe is attracted to every other substance, and the speed of light, or more properly, c, is the absolute speed limit that nothing within the universe can exceed. Planck's constant, on the other hand, is harder to explain. It defines the boundary between what we call classical physics and the quantum realm, so named because at its level, the universe is no longer endlessly divisible, but separated into distinct bits, or quanta. Planck's constant is the amount by which the energy levels of light are separated. Some have referred to it as the pixel resolution for reality. The realization that energy levels were not continuous, but in fact graduated into indivisible levels by a constant amount, led to the discovery of the photon. Max Planck initially devised the idea as a mathematical fudge to make the equations of light work, and then realized it was how the universe actually behaved. The Planck length is Planck's constant applied to gravity, the force that dominates the universe on astronomical scales. That is not to say that the Planck length is the smallest distance to have any meaning, merely that it is the smallest distance to have any meaning within our current laws of physics. Many believe that the scale of the Planck length is where the physics of quantum mechanics and gravity, currently irreconcilable, may fuse, unveiling a new layer of reality. So, what is it? Well, small. 1.616 times 10 to the minus 35 meters. To put that in perspective, if a cubic Planck length were the size of Archimedes' grain of sand, then compared to it, a proton would be the size of the hypergiant star Betelgeuse. Thankfully, I don't have to work out how many there are in the observable universe because someone already has. 10 to the 186. And I'm afraid that number does not have a name, unless you count a Google times 100 septimvigintillion. So that's it, right? Our universe literally cannot be expressed by any larger number. We have reached the end of our journey. Well, no. Remember, the volume we are filling in this thought experiment is merely the observable universe, the fragment of it that light has illuminated for us in its finite voyage since the Big Bang. It does not represent the universe entire. So how big is the universe really? In truth, we don't know. One estimate I read placed the final radius of the universe at 10 to the 10 to the 12th, or 1 followed by a trillion zeros. A number so vast it doesn't matter which units you use to measure it, even Planck lengths. In fact, cubing that number to get the volume would only make it 1 followed by 3 trillion zeros, which is still less than 10 to the 10 to the 13. Others speculate that the universe may be infinite, in which case we really have reached the end of our journey, since any numbers applied to infinity are meaningless. However, it is still possible to map out the geography of an infinite universe, assuming that what is true for our 92 billion light-year wide cubbyhole is also true for the rest of it. As far as we know, there are only 17 different types of subatomic particle, 6 quarks, 6 leptons, including the electron and 3 types of neutrino, and 5 force carriers, including the photon and the Higgs boson. We even have a rough idea how many there are in our observable neck of the woods, 10 to the 86. So that is a finite number of subatomic particles, a finite number of possible positions for them to occupy within a finite space, and a finite number of ways in which they can interact. There are, therefore, only a finite number of ways to combine these subatomic particles within a space the size of the observable universe. And we know what that number is. 10 to the 10 to the 115. That is, 1 followed by 10 to the 115 zeros. That is a gargantuan number. It is larger than a googolplex by a wide margin. It is so large that multiplying it by the number of Planck volumes within it wouldn't change it at all. But it is, as I said, finite. And if you could somehow make the 93 billion light-year leap from one end to the other of our observable universe, and then leap again 10 to the 10 to the 115 times, you would, by definition, end up in a version of the observable universe identical to one you had already passed through. And if you continued to roll these 10 to the 10 to the 115 dice, eventually you would end up in a universe exactly like the one you started in. Everything you know, history, memory, love, death, is simply a matter of different arrangements of subatomic particles. So somewhere beyond the beyond, there is another observable universe, with galaxies just like ours, including a galaxy exactly like our own, which some on the surface of a small blue-green planet somewhere in its suburbs call the Milky Way. And on that planet, in a room just like yours, there is another person just like you, with your name and your memories, listening to someone exactly like me speak right now. In fact, in an infinite universe, there is an infinite number of yous listening to an infinite number of me's. More astounding still, within that number, along with you, me, and everything you know, is every conceivable sequence of events allowed by the laws of physics. Deep in the bowels of that number, not only is the story of Goldilocks and the Three Bears, or the Three Little Pigs, or Little Red Riding Hood possible, they are happening right now. Have you ever dreamed of being James Bond or Elizabeth Bennet? In an infinite universe, somewhere, you are. Keep in mind, these are not parallel universes or alternate timelines. This is the universe we are in, if it is infinite in size. And believe it or not, we can go far beyond even that. All of these potential universes are still constrained by our own paltry laws of physics. A hypothesis proposed by cosmologist André Linde suggests that every time a black hole forms, it creates within itself its own Big Bang, budding off a new universe with its own laws of physics. String theory allows for a landscape of 10 to the 500 potential physical laws, and thus Linde has put a number on the size of the potential multiverse: 10 to the 10 to the 10 to the 7. To be clear, that is not 1 followed by 10 million zeros. It is 1 followed by that many zeros. Even Archimedes had some inkling of these higher possibilities, trapped as he was in a universe far more confined than our own. You see, he didn't stop counting at the myriad order. He continued on, calling the myriad order the unit of the first period, and counting those periods until they too reached a myriad. The final number Archimedes arrived at was 10 to the 8 times 10 to the 16th, which is 1 followed by 80 quadrillion zeros. What was he hoping to count with that number? Did he, looking forward from 25 centuries in the past, have some notion of the potentialities his descendants would one day have to contemplate? Ultimately, when facing the universe in all its cold, incomprehensible magnitude, the true hardest number to contemplate is 1. To set oneself alone against the yawning expanse of the black abyss we call home can be a daunting task. And that is why I must thank you, my 10,000, for accompanying me on this journey, and I hope we will continue to take many more in future.